Welcome, everyone. I hope you're all doing well. Looks like we got most of you guys to take that first test. I'm missing 2 grades, but I think the people that didn't take it haven't really been coming to lecture, so I don't know. It's not your problem. But the grades have looked pretty good, so nice job. The tests will be a similar format from here on out, so multiple choice. Your next test will be coming up October, not until October, I think 17th and 18th. So you've got about a month. So we're going to move into the next section, which is going to be chapter 5, chapter 9, and chapter 10. We skip chapter 6, 7, and 8. Don't you worry, we're going to come back to it for our third test, but we're going to deviate away from math a little bit, and then we'll go back to math. So not so heavy on the calculator this time, more on concept stuff. Chapter 5 is all on molecules and compounds. So we can kind of think of this as like the words of our language. So the elements were the letters, the molecules and compounds will be the words, and then at some point in chapter 6, a little bit later on, we'll move into the sentences of our language, which will be for chemistry, chemical equations. So sugar is composed of carbon, hydrogen, and oxygen. Sometimes it's referred to as sucrose. It's common name. Sugar has much different properties, like much varied properties than our carbon, hydrogen, and oxygen. Carbon, which makes pencil lead and diamonds, hydrogen, which is a poisonous flammable gas, and oxygen, which is a gas that we breathe. So none of those sound very appetizing. Right? Sucrose, when they come together in this very specific combination, now have this new set of properties that is sweet, and that our body can break down into fuel. The properties of sucrose are very different from the properties of the elements they contain. A lot of times people will kind of get what the elements are mixed up with the compounds. So there'll be a formula like aluminum sulfate. And they're like, oh, well, that's probably shiny like aluminum, right? Because it has aluminum in it. No, aluminum sulfate's properties are much different from aluminum. So another example, sodium and chlorine. So when you hear me say, hey, sodium on the periodic chart, I am not talking about table salt. I'm talking about a dull metal that's extremely reactive. Okay, chlorine is a yellow gas that is reactive, and it's also poisonous. Both of these things, not very appealing, but when they come together as sodium chloride, you get table salt. The properties of the compound in general are different from the properties of the element they compose. So don't assume that just because it contains something, it will be like that. There are lots of materials that contain silver that have none of the qualities or properties of simple silver. They are now a new material. So some of the substances that you guys interact with in everyday life are elements, graphite in your pencil if you have like a true diamond ring. But most of the things that we come into contact with are either compounds or mixtures, usually compounds. Why are free atoms or free elements so rare in nature? Because most of the elements on the periodic chart are relatively unstable. They don't have a full electron configuration or a full outermost electron shell. So they like to combine with other things to create stability. When they combine with other things, you get a compound. It is important to remember the difference between a compound and a mixture. So in a compound, the elements are combined in fixed definite proportions, meaning I can write a chemical formula for it. I can't change the proportionality, like the compound water, H2O, 2 hydrogens for every 1 oxygen. That is non-negotiable. That is what water is. A mixture, on the other hand, can have varying proportions, and the things aren't chemically bonded to each other. So salt, water. The salt in the water molecules are not fused together. They just happen to be occupying the same container, and they've distributed amongst each other. Could I add more salt? Yes. Could I add more water? Yes. That's what a mixture allows us to do. Here's another example. We've got two balloons here. They both contain hydrogen and oxygen, but on the left, the hydrogen and the oxygen are a mixture. So they're not fused together. So I have some hydrogen molecules, and we'll talk about why there's two of them in a little bit. And we have these oxygen molecules. Could I pump in just solely more hydrogen? Yeah, definitely, and change the ratio of these two. On the right, we have a water balloon that contains hydrogen and oxygen as well, but they're fused together in a specific ratio of 2 hydrogens for every 1 oxygen. If I put more water in there, do I change the proportionality? No, it's still going to be 2 hydrogens for every 1 oxygen. Can I add just hydrogen or just oxygen? No, not if I want to continue to classify it as a water balloon. It would then be a mixture of weird things, of a gas and some water. So this idea of constant composition, to expand on that, Joseph Proust came up with this statement that says all samples of a given compound have the same proportions of their constituent elements. So whether I have 1 water molecule or I have an entire swimming pool of water molecules, it will always be a 2-to-1 ratio of hydrogen to oxygen. That is its recipe. If we decided, oh, we're going to make it H3O, that is no longer water. We cannot call that compound water. We would call that something else. So you have to respect the proportions of whatever the given compound is. How many compounds are there in the world? So many. And they're making new ones all the time. Okay. So one way to identify and write compounds would be to memorize them all, which would be insane and ridiculous. The other one is to do this thing called nomenclature, which we're going to start to go through. And nomenclature is the process of naming using a system. All right. So I'm not going to teach you every compound. I'm just going to teach you the system to name the compounds. If there was a chapter that I could say, this is the most important chapter in the class, this is it right here, chapter 5. Okay. On your final, I think you'll end up having like 50 questions, like 8 to 10 of them are directly related to this chapter. All right. And it's hard to do the next chapters if you don't have this stuff down. So if there's a chapter or a time where you're like, you know what, I'm just going to suck it up and I'm going to like study my butt off, this is the chapter to do it. Okay. I don't really test you guys on this, but there's also a mass ratio. We will come back to this later, but the idea is that for any given sample of a given compound, the mass ratio will also be the same. Even if you have a large quantity or a small quantity, the mass of, let's say, the oxygen in water will be related to the mass of the hydrogen in an 8-to-1 ratio. Okay, 8 grams for every 1 gram of hydrogen. Nitrogen or ammonia has its own relationship between nitrogen and hydrogen. Again, I'm not spending a whole lot of time with number stuff. We'll kind of revisit this in chapter 6 later on. So how do we represent a compound? Well, we said in order for it to be a compound, it has to have, you have to be able to write it as a chemical formula. And so the chemical formula is going to express what elements are present in the compound. And it's also going to tell you how many of each you have. So we've got this guy here, H2O, which hopefully you kind of like know that's water. If not, that's okay. This is the molecule water, the compound water. So we have 2 elements present. We have hydrogen and oxygen. Nothing else is in there. Argon isn't written because we don't have it. So you don't put elements down that you don't have in the compound. There is a subscript here, and the subscript tells me how many of the hydrogen atoms I have, or the thing that sits right before it. Oxygen only has 1, so we just imply a 1. I don't write H2O1, I just write H2O. So if you have only 1 of something, the symbol is indicative enough that you've got it present as 1. Good time to separate a subscript from a superscript, because this seems to always mess people up, but O2 minus, okay, this is a superscript. meaning it's sitting above like the middle ground of where the letters are. Superscript is talking about charge, specifically superscript on the back end. If you had a superscript on the front end here, this would be the mass, the atomic mass for like an isotope. Subscript is talking about number of atoms. So subscript, which this one is just an inferred one, is number of atoms. So if I write something like this, this is sulfate, this is polyatomic ion, SO4 2 minus. Okay. There is 1 sulfur, there's 4 oxygens. The subscript tells me how many oxygens are. The superscript tells me what the charge is. The overall charge is 2 minus. So you want to separate those things out. Sometimes people will get those flip-flopped. They'll like want to drag the 4 up with the 2 or bring the 2 down to the 4 or flip them or whatever. Keep those separate. Anything sitting above in a superscript charge, anything below subscript is the number of atoms. All right. So again, how many? Oh, go away. I don't want you anymore. Didn't want to lose all of it. So again, how many compounds are there? There's so many compounds. Here are some common compounds: NaCl, which is table salt or sodium chloride. Table salt would be its like common name. Sodium chloride would be its nomenclature name, its systematic name. It has a ratio of 1 sodium for every 1 chlorine. That is what makes table salt. If there were more or less or different things, it would no longer have the properties of salt. Carbon dioxide, CO2. 1 carbon for every 2 oxygens. They can get big. So sugar is C12H22O11. The ratio is 12 carbons to 22 hydrogens to 11 oxygens. We just look at whatever that subscript is and attach it to the elements symbol that's coming before it. The subscripts in the chemical formula are just as important as the elements present. So you never want to change them. You always want to honor what the subscript is supposed to be. A great example of that is like, let's say I said, I wanted you to write carbon dioxide and you're like, well, that's carbon and oxygen, right? So I'm just going to throw carbon and oxygen and you forget that subscript. You've not made carbon dioxide. This is carbon dioxide over here, carbon with 2 oxygens. This is carbon monoxide, carbon with 1 oxygen. Oh, what's the big deal? Well, carbon dioxide is a relatively harmless gas that we exhale and plants breathe in. Carbon monoxide is a pollutant and a poisonous gas that you probably have carbon monoxide detectors in your house you don't want to have in high quantities. So we never want to just like forget about subscripts or ditch them or drop them. They're important. So with table salt, you'll see that it's written as NaCl and not ClNa. This looks very weird to me. It may not like instinctually look weird to you because you haven't been doing a whole lot of chemistry, but this is the way we'd want to write it. And why is that the case? It's because if we have a metal and a non-metal, we're always going to write the metal first and then the non-metal second. Okay. So if you're like, well, what was a metal again? I totally forgot. Let's go to periodic chart. Remember your zigzag line. If it's down and to the left, all of these are metals. If it's up and to the right, non-metals. So that's why we write sodium and then we write chlorine. You'd never want to put this guy before one of your metals. What happens if you have 2 non-metals? All right, we're going to have to skip back over there. If you have 2 non-metals, the thing that's more quote unquote metal-like gets listed first. So the thing that's closer to the zigzag line gets listed first. If you don't have a periodic chart with you or out, grab one because we're going to be looking at it a lot for class today. So I don't have to hop back around, but let's look at, like, it looks like they are using nitrogen and oxygen. So this would be nitrogen dioxide. They're going to put nitrogen first before they list oxygen because nitrogen, again, is closer to that zigzag line. It has slightly more metal-like properties. Is nitrogen a metal? No, it's not, but it exhibits more metal-like properties, and they have to come up with some sort of system. So this is what they've decided, okay? Same thing with sulfur and oxygen. So if you look, sulfur is below oxygen, meaning it's closer to the zigzag line. So we're going to say SO2, not O2S, because we want to follow the system. Are there exceptions? Oh my gosh, there's always exceptions to every rule. That's just how it goes. I'm not going to test you guys on exceptions. You do need to know this one. This is hydroxide, and I will show you guys more of that when we get into polyatomic ions. But in this case, we list O first and then H. Here's a system of the nonmetals in their ordering. So carbon will come before phosphorus, become before nitrogen, hydrogen, so on and so on. Really, in general, if you kind of just follow the closer to the zigzag line, you should be okay. So that thing, OH, is a polyatomic ion, which sounds scarier than it actually is. Come on. My pen is giving me a really hard time here. So polyatomic ion. What does poly mean? Multiple, more than one, many. A polytheist, believes in multiple gods. A polygamist, has multiple spouses. So many or more than one. Atomic is an atom. And then ion means that it's charged. So an example of this would be the sulfate ion. Sulfate. Sulfate is SO4 with a 2- charge. Okay, one sulfur with 4 oxygens, and you can kind of think of it like a packet. Okay, a packet of elements that are gonna, for the most part, stay together. Yes, there are chemical processes that can strip this thing apart, but a lot of times it kind of just behaves as a unit. And this whole unit has a -2 charge, right? So that -2 applies to the entire packet. So I even have students in the beginning kind of get in the habit of just circling where the atoms are and then letting the charge sit on the outside so you know that it applies to the entire thing. All right, so when sulfur comes together with 4 oxygens, it'll have a 2- charge and it'll be called this thing, sulfate. Polyatomic, multiple atoms with a charge, ion. So you will see sometimes these polyatomic ions in compounds, and you need to be able to identify how many there are. This thing here is magnesium nitrate. It's magnesium with nitrogen, oxygen, combined as a polyatomic. Now, if we have more than one of these polyatomic ions, we have to represent it by putting parentheses around it and then putting the multiplier on the outside. So in this case, you can think of it as being 1 magnesium, and it's combined with 2 of these nitrate ions. So whatever the subscript is on the outside of the parentheses, you have to multiply it by the subscripts on the inside. So nitrogen is actually, there's going to be 2 of them because there's 2 of these packets. Oxygen, there's going to be 6 of them because there are 2 of the packets, and each packet contains 3 nitrogens. If I draw like a really rough sketch, nitrogen, oxygen, 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 we'll stick it together. Here's another one, nitrogen, oxygen, oxygen, oxygen. Okay, so if I have 2 of them, how many nitrogens do I have? 1, 2. That's where the 2 is coming from. If I have 2 of these packets, how many oxygens do I have? 1, 2, 3, 4, 5, and 6. I wouldn't recommend drawing them out. Just get in the habit of multiplying, okay? Whatever's outside the parentheses by whatever's inside the parentheses. So I'm gonna give you 2 formulas, and I want you to tell me how many of what atoms are present, and then how many of each atom is there. So let's do aluminum sulfate, which is Al2 parentheses SO4 3. And then let's also do P2, no, not P2. Ah, sorry. Al2, SO4. I didn't mean to get rid of everything. 3, and then let's do, oh, my brain. Come on, Candace, work. Ca3, EO4, 2. Let me give you one that's a little bit more challenging. All right, so for each of these compounds, you don't need to know what the name of them is yet. Just tell me what atoms are present and in what quantity. Okay. All right, so for this first one over here, we've got aluminum, we have sulfur, we have oxygen. The aluminum's easy to see. There's no parentheses. It's not like in some sort of packet. So I just know that I have 2 of them. Sulfur is not just existing as sulfur. It's existing as the sulfate ion. So I need to take into account not just how many sulfurs are within each sulfate. In this case, it's 1, but I also need to multiply it by how many packets I have, 3. So we'll take 1 times the 3, or we'll have 3 sulfurs. Oxygen within the packet, if it's sulfate, I will have 4 oxygens, but I have 3 of those packets. So I need to multiply it by 3, or I'll get a total of 12 oxygens. And if you're thinking, oh, that seems like a really big number, you can get larger numbers with what these are. Sometimes instead of cutting it into sulfur and oxygen, you may see it written as like SO4 2-, like a packet, and it'll say, hey, how many packets do I have? And you'll say, oh, well, I have 3 packets. This one over here, this is calcium phosphate. We have calcium. I have 3 of them. Phosphorus, well, I have 1 within the packet, but I have 2 of those packets. So I'm going to take that 1 times the 2 packets to give me a total of 2 phosphorus. And then oxygen, there's 4 within each packet, but there are 2 packets. So I need to multiply that out by 2 to give me a total of 8 oxygens. And again, sometimes instead of separating these out, they'll write them as, PO4 3-. Hold on 1 second, Betty. PO4 3-, and then we'll say, hey, we have 2 of those. What's up, Betty? You have to turn your mute off.
The P is always times 1, correct?
Well, in this instance, there's 1 phosphorus here. So that's why I'm going to say it's times 1. There's 2 on the outside. So in this specific instance, there's 1 phosphorus, but it's not in every instance. You just have to be able to read whatever is written there.
Okay. Thank you.
Mm-hmm. So one person, very smart, getting ahead of the curve here. Betsy said, if I may, the -3 charge and the -2 charge doesn't show itself in the formula here. Where did I get that from? Because I have my polyatomic ions memorized. And so will you too. Or you'll have a polyatomic ion sheet. And I will show you guys in a minute where you can kind of reference that. There's one in your text and there's also one in the slides. I just know these, like I could list off polyatomic ions in my sleep. I probably do. So hopefully you will get to that point as well. All right. Let's get back to the slides. So this is something we'll kind of lightly talk about now, and then we'll expand a little bit more in chapter 6, but there are a couple different types of formulas. Everything that we've been looking at thus far has been what's known as an empirical formula. And an empirical formula is the relative number of atoms in each element meaning it's the lowest ratio of them. A molecular formula will give the actual number of atoms. It's a multiplier of the empirical formula. Now, a lot of times with inorganics, what we're studying in this class, the empirical and the molecular formula are the same. Okay, so the molecular formula for lithium sulfate is Li2SO4. So I can't reduce that down because this is a packet. Okay, that has to stay intact to be sulfate. So I can't reduce that down. So the empirical formula is also Li2SO4. Now, one that has a different, okay, molecular and empirical formula, hydrogen peroxide. In real life, if you were to be able to see those cute little molecules, it's 2 hydrogens for every 2 oxygen. All right, like 2 little pairs. So there's 4 atoms floating around together. That would be its molecular formula. The empirical formula, though, is the lowest ratio. So I can divide both of these by a factor of 2, which would give me HO. Again, this tends to be more applicable with organic compounds when they get really big and clunky. So let's say I've got the molecular compound, or rather the molecular formula of C22H33O11. Okay, some made up compound. I want you to tell me, what is its empirical formula? If that's the molecular formula, what would be its lowest ratio? Give yourself 20 seconds to maybe think that out. So going from the molecular to the empirical formula, can I divide these all out by something? Yeah, each of these can actually be divisible by 11. So the lowest ratio is going to be 2 carbons for every 3 hydrogens and every 1 oxygen. Going from the empirical formula to the molecular formula takes more work, and we will do that in another chapter. But for now, I just kind of want you to know the basics of an empirical formula is the lowest ratio. The molecular formula is what's actually happening. Now, if you look at water, the molecular formula for water is H2O, which is also the same thing as its empirical formula. What's happening in real life is also the lowest ratio. Doesn't always happen, but a lot of times it happens. A structural formula is a way of taking our written formula and writing it in like space on a piece of paper, so we can have a placement for everything. So methane, which you would not need to know how to name because that's a organic compound, but methane, the CH4, this is its molecular formula. Its structural formula looks like this. I put carbon in the center and hydrogens on the sides. And I will teach you in a chapter or 2 how to draw these structural formulas. So don't get freaked out now if you're like, I didn't know the carbon was supposed to go in the center. Just trust me for now that that's sort of the setup. This gives me a sort of a relative idea of where the atoms are. We can also have them drawn as these ball and stick models that are 3-dimensional, or these space filling models. I am not good at drawing, so these things I usually don't do. I tend to stay with this sort of flat shape, and you just have to extrapolate the 3-dimensional qualities of it. So, all right. So looking at compounds and elements, because remember we talked about matter being divided into either a pure substance or a mixture. And then when we go into pure substances, we can say it's either an element or it's a compound. Well, we're actually going to divide that down even farther. So I'm going to take, so here's pure substances, and you could put this limb up to matter as a whole, and over here are mixtures, and we're not going to deal with homogeneous or heterogeneous mixtures for this. We're just looking at pure substances. So if pure substances is divided into an element, meaning it's made of one type of atom, or a compound, it's multiple types of atoms. The element can further be divided into what's known as an atomic element or a molecular element. And sometimes this word molecular is replaced with diatomic, a diatomic molecule. Does anyone know the root of di? Di being 2, okay? So in a diatomic molecule, what you're getting, well, I guess let's go with the atomic first. That's the simplest. That's just when you have atoms and their most basic unit is going to be an individual atom. A molecular element or a diatomic molecule is when the basic unit is a pairing or there's two of them. So oxygen, for instance, I would never write oxygen as element in an elemental form as just O. I would write it as O2 because oxygen likes to pair to another oxygen. It makes it more stable. So how do you know which ones create a diatomic molecule and are molecular and which ones are atomic? You memorize it, or you give yourself some notes on your formula sheet. So mercury is an example of an atomic element. The base unit is single mercury atoms. Chlorine is a diatomic. Its base unit is two chlorines paired together. That's why it's called molecular, because its most basic shape is a molecule, meaning it's more than one thing. These are the diatomics. All right, have no fear of ice cold beer, but cold is chlorine, not carbon, and beer is bromine, not boron. You look at your periodic chart, go to hydrogen. Hydrogen is a diatomic. Let me pull up this formula sheet over here. So my diatomics are going to make kind of an upside down L. Hydrogen over here. Then we're going to skip boron and carbon. We go to nitrogen, cut over and down to iodine. Those are all diatomics. So it'll be H2, N2, O2, F2, Cl2, Br2, and I2. So if you know those are all the diatomics. Everything else is atomic. That's it. Yeah. You go process of elimination. So if it isn't one of these in your L, including your hydrogen, it is atomic, or its most base unit is an atom. This will come back to bite you in the butt later when I'm like, hey, chlorine mixes with nitrogen. You can't just write chlorine as Cl. You have to write it as Cl2 because it likes to pair with itself. Okay, so note on a periodic chart somewhere, and you lucky dogs get to use your notes as opposed to my in-person class. I have to memorize all these. So make a note with the diatomics. All right. The next thing we're going to do is talk about, so we've got our atomic, that's mostly everything. The diatomics are your have no fear of ice cold beer. Compounds we can divide into two different groups. They can be either molecular or ionic. Okay, an ionic compound means that it has an ionic bond. An ionic bond is when a positively charged thing and a negatively charged thing stick together, or they transfer electrons. Write a note that says ionic is a metal combined with a nonmetal, or a metal combined with a polyatomic ion. If you have two nonmetals, it's going to be molecular. So H2O is a good example of a molecular compound. Hydrogen is definitely not a metal. Oxygen is not a metal. So we go with molecular. How do these differ from each other? Well, this here, the ionic, transfers electrons. Here in the molecular, they share electrons. So molecular compounds are compounds formed by two or more nonmetals. Ionic compounds contain one or more cation anion pairs. In most cases, the cation is a metal and the anion is a nonmetal. Sometimes the anion can be a polyatomic ion. So I'm going to write out a couple formulas, and all I want you to do is tell me whether it's molecular or ionic, because the way that you name these things and the way that you write the formula is based off of this. The way we do it for ionic is totally different than the way we do it for molecular. So if you cannot identify the difference between those two, you're starting from a bad place. You're probably not going to name the thing correctly. Let's make up a couple here. And again, you don't need to name it. I just want you to tell me if it's ionic or molecular. So Al2O3, MnF2, C4Cl2. Sorry, I'm like making these up as I go along. CaOH2, FrBr, and CO2. Okay, so tell me whether these are ionic or molecular. All right. So what I find sometimes is that students, like when they're naming this, they forget to classify it as ionic or molecular, and it makes everything else more difficult. And then when I say, hey, is this ionic or molecular? They're like, I don't remember how to do that. Ionic means that there's a metal and a non-metal. It's that simple. It's almost so simple people forget. So is this a metal, this first thing? It is. So this is ionic. Next one, and this is a non-metal. And remember, we list the metals first. So really, if that first thing you bump into is a metal, you can kind of go, it's ionic. This here, manganese, that's a metal, and this is a non-metal. So this is also ionic. This here, first thing I bump into is carbon, that's non-metal. And you know what, chlorine's also a non-metal. So this is going to be molecular. The way that I name this and handle and manage this is going to be different than the way that I deal with the first two. This next one here, this is ionic. That first thing that we're seeing is calcium. I know there's like more than just two atoms in here. This is a polyatomic ion, and we'll get into it in a little bit, but it's a metal combined with some non-metal things. So it's ionic. This, metal, non-metal, ionic. This here, non-metal, non-metal, molecular. Does that feel simple? I want that to feel simple. I want that to be like easy. Okay, yeah, I can identify if it's ionic or molecular. Because if you can't identify it, you have a 50-50 chance that you're going to name it wrong. All right. Cynthia, you said the ionic, this was a couple minutes ago, sorry. You said the ionic compound was a metal with a non-metal, and a molecular is two non-metals, two or more non-metals. Okay, so CO2 is a good example of something that's molecular. Two non-metals. The reason it's called molecular is because its smallest unit that's still identifiable as carbon dioxide is a molecule. It's a carbon with two oxygens, and it makes this like little packet. Ionics are a little bit different in that their base unit is what's known as a formula unit. So it's going to be sodium chloride, which is salt, will be a sodium and a chlorine next to each other, but it makes this three-dimensional lattice structure. So every chlorine is really attached to a sodium above, to the side, below, right, and left. And that's why salts tend to make these really nice uniform structures, whereas dry ice, which is frozen carbon dioxide, makes a much more irregular shape. So last chapter, we talked about how metals like to give up electrons or lose electrons to form a cation. A cation is something that's positively charged. Nonmetals have a tendency to gain electrons, or they form an anion, which is negatively charged. What do positive and negatively charged things like to do? They like to stick together, okay? Like a positive and a negative end of a magnet will stick together. So what's happening here in an ionic compound is one thing is giving up electrons and it becomes positive. Another thing is gaining the electrons, it's becoming negative, and they are now attracted to each other. Makes an ionic bond. Or you get this transfer of electrons. So when you want to write a formula for an ionic compound, these are some things you want to do. Review the elements and their charges. Ionic compounds will always contain a positive and a negative ion. In the chemical formula, the sum of the charges of the positive cation and the sum of the charges of the negative anions need to equal each other, or the overall formula will have a neutral charge. That's why they're coming together, okay? That's why something positive and negative are coming together. They neutralize their charge. So a couple notes you can say with ionic compounds, they should always be charge neutral. They will always contain a metal and a non-metal. Let's review our charges. So where did you go, charges? Okay, so remember in column 1, I put 1 plus. Over column 2, I had 2 plus. You guys were just going to trust me on this, right? Aluminum is 3, 2, 1. And then we had above nitrogen, I don't know why they don't have it on here, but this is a 3 minus, 2 minus, and fluorine is a 1 minus. And then over the noble gases, you put like a 0 with a strike through it because those don't really form ions. So we've got some things that like to form positive charges. Do you see all these ones in here that don't have a charge written on them? Those are transition metals. They are sort of a pain in the butt in that they can have a variety of charges. We will get into that a little bit later. Let's work with the simpler one first. So the system for writing the formula goes as follows. Write the symbol for the metal and its charge, its predictable charge. Write the symbol for the nonmetal and its charge. And then make the magnitude of the charge of each ion without the sign become the subscript of the other ion. Oh my gosh, that makes perfect sense, right? No, so what you're going to do is take the numbers and you're going to flip-flop them to the subscript of the opposite thing. Why are we doing that? That's the fastest way to get a charge neutral molecule. If possible, reduce the subscripts to give a ratio with the smallest whole number. Check and make sure that the sum of the charges equal each other. Let's look at an example. I feel like it makes more sense if we look at something. So aluminum. We're going to make aluminum oxide or aluminum and oxygen. So I take aluminum, and I know that aluminum likes to form a 3 plus charge. Does it form a 2 plus or a 1 plus? No, it's always going to form a 3 plus. So we're going to put 3 plus there. Oxygen likes to form a 2 minus charge. So I'm seeing, okay, this is a metal, this is a non-metal, this is ionic. I'm going to do my flip-flop. What I take is the number from the aluminum, not the charge. We're going to ignore the charges. I'm going to take the number from the aluminum and put it as the subscript of the oxygen. And then I'm going to take the number of the oxygen's charge, and I'm going to make it the subscript of the aluminum, or I flip-flop charges for subscripts. You guys seen how that's happening? Why do we do that? Because it's much faster to do it that way than to say, well, aluminum has a 3 plus charge and oxygen has a 2 minus charge, and their lowest common ratio would be 6. So I need to have 2 of these to have 3 of these. It's just easier to flip-flop them. Let's double check and make sure that this whole molecule is charge neutral. Like it doesn't have a charge in the upper right-hand corner, but we're going to double check. Aluminum always has a 3 plus charge, right? And we're saying that there are 2 of them. So I'm going to multiply that by 2, which is an overall 6 plus charge coming from the metal. Oxygen has a 2 minus charge. How many are there? Well, we're saying that there are 3. Okay. So that gives us an overall 6 minus charge. Look at that. 6 plus, 6 minus will give us 0. So that's the fastest way for us to find a charge neutral molecule. I don't know why they don't complete this one on the slides, but magnesium and oxygen. So magnesium has a 2 plus charge. Oxygen has a 2 minus charge. We're going to flip flop. All right. This will get a 2 and this will get a 2. Now, the last thing that it said on the other slide was if you can reduce it in ionics, metal, non-metal, if you can reduce it, reduce it. So can I reduce the 2 and the 2? Yeah, we can divide both of those out. So this is actually MgO. That is how magnesium and oxygen will come together. Will magnesium and oxygen ever come together in a different way? No, because magnesium's charge is always 2 plus, oxygen's charge is always 2 minus. So when you flip-flop the charges for the subscript, you're always going to find that ratio. Doesn't matter what piece of paper you write it on, doesn't matter what pen you use, it's always going to have those charges to flip-flop and get you that 1-to-1 ratio. So let's do a couple of these. Any questions on that? On why we're flip-flopping, on what we're flip-flopping? We're not taking the charge, we're kind of just ignoring the charge. We're just taking the number and dropping it down to the opposite guy. All right, leave you alone, polyatomic ions, for a minute. So we'll walk through one together. We're going to mix, let's mix calcium and phosphorus. Okay, calcium. I'm going to mix that with phosphorus. I don't want to say mix. Okay, we're going to bond it to phosphorus. So let's go through this. We'll do this one together step by step, and then I'm going to give you some on your own. So when you come across calcium and phosphorus, the name of this thing would be calcium phosphate, and I will calcium phosphide, and I will teach you that in a little bit. But for now, we want to combine calcium and phosphorus. This is a metal and a non-metal, so I know I'm going to need to flip-flop charges to make a charge-neutral molecule. So I'm going to write the symbol of the metal first, calcium, and I'm going to include its charge. All right, look at your periodic chart. Where does calcium sit on your periodic chart? It's in the second column. So it should have a 2 plus charge consistently. It's just what calcium does. Phosphorus, the symbol is P. It's sitting in column 1, 2, 3, 4, 5 of the main groups. Above that column, you should have put a 3 minus. If you didn't, put a 3 minus. So nitrogen and phosphorus like to form the 3 minus charge. Now, what I want to do is take this 2 and stick it on the bottom of the phosphorus, and take this 3 and stick it on the bottom of the calcium. Or I'm going to have 2 calciums for every, sorry, ignore me. Ignore everything I just said. Not everything, just the last little bit. We're going to have 3 calciums for every 2 phosphorus. That, what I just did is a super common mistake I see with students is they'll go, oh, well, here's a 2. I'm just going to drop the 2 straight down to the calcium. No, we need to flip-flop. Okay, so the 2 gets put as the subscript for the phosphorus. The 3 gets put as the subscript for the calcium. Let's like beat a dead horse and check and make sure that it's charge neutral. Calcium, well, we know it has a 2 plus charge, and there's 3 of them times 3. That gives me plus 6. Phosphorus has a 3 minus charge. And there are 2 of them. That's 6 minus. Those 2 are charge neutral. Okay. Any questions on that before I give you guys a bunch of things to mix together? All right, I'm not going to go by their formal names yet because you don't know how to do that, but I'll just give you couple different things. So let's take potassium, and we're going to combine that with oxygen. Then let's take magnesium, and let's combine that with sulfur. Let's take sodium. We'll combine it with phosphorus. And then let's take silver, combine it with chlorine. And just for fun, I'll give you one other thing. Let's take titanium. And combine it with oxygen. Don't spend too much time on this. Hint, hint, wink, wink, you can't do it, okay, currently. So, but maybe come up with a reason for why you can't solve this one. But the first ones, first 4 you should be able to do. I'll give you guys about 5 minutes. Set it up the way that I showed you. So first write the metal with its charge, then write the non-metal with its charge and flip flop. Obviously, as you get better with the system, you won't have to go through that whole process. Like I don't need to do that. I can just write the formulas because I'm so used to the charges. But for now, be real anal about that because it is a lot of like detail stuff. So I'll see you guys in about 5 minutes. All right. So we're combining these things together. Potassium, well, first of all, you always want to check and make sure that it's a metal and a non-metal, or a metal and a polyatomic ion. If this happened to not be a metal and they were 2 non-metals, we don't use this system. But for the sake of time, these are all metals. So we know we're going to do this flip-flopping process. Potassium is K, and it has a +1 charge. Oxygen, O, and it always has a 2- charge. Those are non-negotiable. That's just what the charges are. So now we're going to flip-flop. I need to have 2 potassiums to balance out 1 oxygen. And if you think about it conceptually, right, oxygen has a bigger negative charge than potassium, 2 of these guys to balance this out. Or the 2 gets dropped to the potassium, K2, and the 1 gets dropped to the oxygen, K2O. That's how potassium and oxygen will always come together. Magnesium and sulfur. Magnesium is Mg. It's in column 2. It always has a 2+ charge. That's what it is. You will learn in next chapter, I think, or the chapter after that, why exactly magnesium likes to form a 2+, but for now, you're just going to trust me. Sulfur, which is in column 5 of the main group elements, that tends to form a 3- charge. So flip-flop, it means I should have 3 magnesiums, right? The 3 comes down here for every 2 sulfurs. Sorry. I don't know where my brain is today, guys. I'm sorry. Let me backtrack a little bit there. Sulfur does not have a 3- charge. Sulfur has something didn't feel right. 2- charge. Okay, flip-flop. Mg, testing your skills, 2s2. We'll reduce those down to 2 and 2, and we get MgS. Like that doesn't look right. All right, sodium and phosphorus. So sodium is in column 1. It always forms a +1 charge, just like potassium, right? These guys are similar to each other in their charge formation. Phosphorus, I think that's what I was looking at, phosphorus, but I saw sulfur. Phosphorus's symbol is P, and it is a 3- charge. Okay, flip-flop, I would need 3 sodiums to balance out 1 phosphorus. Silver and chlorine. Silver, which symbol is Ag, always forms a +1 charge. I told you aluminum was 3+, zinc was 2+, silver was 1+. So make sure you have that in your little boxes. So silver has a predictable charge of 1+. Chlorine is always 1-. So when these 2 things come together, it's a 1-to-1, or AgCl. This one here that I said you're not going to be able to solve. Why is that the case? So titanium and oxygen. So I know I have titanium and I have oxygen. Oxygen is a 2- charge. What is titanium's charge? I don't know. I can't tell its charge from its position on the periodic chart. Those transition metals can have multiple charges. Titanium could have a 2+ charge. It could have a 4+ charge. The way that it is currently written, I don't know what its charge is, so I can't come up with a formula. Okay, the writer would have to give you more information, and I'll show you that in a little bit. Are you guys feeling okay with the flip-flop minus my flop here? Metals, non-metals, flip-flop charges. What if instead of a non-metal, we have a polyatomic ion? It's going to follow the same system. It may look a little bit scarier, but it's the same system of flip-flopping. So first of all, let's look at some of the polyatomic ions. Here is an appendix that's in your text. You can find them online as well. Like you could do a quick Google search and say polyatomic ion list, and you'll see the similar ones coming up. Are there more polyatomic ions than here? Yes. These are the most common ones. The ones that I have my students in person memorize because we use them so often are like acetate, carbonate, hydrogen carbonate, hydroxide, nitrate, nitrite, phosphate, ammonium, sulfate, sulfite, and cyanide. We tend to see those ones a lot more. All right. You, again, don't have to really have them memorized because of the nature of the class. But you do need to be able to reference them and just know that those will probably come up more often than the other ones. So when we're talking about acetate, acetate has a formula of 2 carbons, 3 hydrogens, and 2 oxygens. And this whole thing has a -1 charge. The charge on your polyatomic ion is just as important as the number of atoms, right? Sometimes people get real stuck with like, oh, carbonate, it's 1 carbon and 3 oxygens. That's all that I need to know. No, you need to know carbonate has a 2- charge. Why? Because the charge tells us how many of the metal we need to balance it out. So you've got to have the charge number. What I see happen a lot too, it's like, for instance, carbonate, which is CO3 2-. Sometimes people will like transmutate this 3 and 2 and they'll write CO2 3- or CO23- or all sorts of weird things. Keep the 3 with the oxygen, keep the 2 with the charge. It's just, I mean, you guys get to have an appendix, so I'm not going to beat a dead horse here. My students in class have to memorize them. You won't have to do that. So let's talk about flip-flopping. If we are going to combine these, and most of the time, do you guys see how every one of these has a negative charge? Except for ammonium. Ammonium has a positive charge. So ammonium is the one that will take the metal's place. Okay. All the rest of them, because they have a negative charge, all of these guys will take the non-metal's place. Metals place. So do one together. Or I don't know, do the slides have an example? Maybe they have an example. No, they don't have an example. Okay, well, boo-hoo. We'll come up with one. So last time you were combining metals with nonmetals. Now we're going to combine metals with polyatomic ions. I'm not going to write the formula or the formula for the polyatomic ion. I want you to reference it. So if you've got a cell phone close or you have your computer, go ahead and look up what the polyatomics are. But I'm going to have you combine, let's combine aluminum with something called nitrate. You get to discover what nitrate is. Let's combine zinc and sulfate. Let's combine calcium and nitrite. And then let's mix up, what do I want to do? Sodium with phosphate. I'm going to do the first one with you guys, and then I'm going to do one more, write one more out here. Let's do barium and carbonate. Okay, I'm going to do this first one with you. So we're combining aluminum and nitrate. Aluminum is just aluminum, Al3+. Nitrate is a polyatomic ion, and you may be saying, well, how do I know that that's a polyatomic ion? It kind of looks like the word nitrogen. Is it just nitrogen? I mean, it contains nitrogen. A good indicator it's a polyatomic ion. If the ending is ATE or ITE, those are polyatomic ions, okay? ATE, ITE, good indicator it's polyatomic ion. So you're just going to want to reference that. So nitrate is this thing where we have one nitrogen combined with 3 oxygens, and that whole packet has an overall -1 charge. So I sort of like my students in the beginning to get in the habit of circling, again, the atoms, leave the charge on the outside, circle the atoms, so you create a unit. And whatever we do to the nitrogen, we have to do the oxygen, we do it as a whole. So when I flip-flop charges, the 3 here needs to encompass the entire nitrate molecule. I have 3 of those nitrate molecules. So how do I do that? Well, I'm going to put the nitrate in parentheses, okay? The charge here is a 1, so that's going to say 1 aluminum, right? That one's pretty easy to do. The 3, again, needs to wrap around the nitrate, so I'm going to write it as parentheses NO3 with a 3 on the outside. So the 3 has come here. The 1, I'm going to move it up and over, has come down here. What are some common mistakes that I see with this? I'm going to write it in red so you don't do it. People will write aluminum and they'll be like, oh, it has a 3+ charge, so I must have 3 of them. And then I have a nitrate. Okay, no, we need to flip-flop. What's another thing I see people do? They'll get the idea that there's 1 aluminum, and then they'll get to nitrate and they'll see, you know, that there's a 3 here and a 3 here. And they're like, oh, okay, so it's just NO3. They get like weirded out by there being 2 3s next to each other. That's not what's happening. We don't have 1 nitrate. We have to have 3 nitrates. Another thing I see people do, AlNO3 3, and they won't include the parentheses. Why is that wrong? We definitely don't have 33 oxygens, okay? We want to say that we have 3 of the packet. So start to treat this thing again as a unit or a packet. So if it helps, circle and then, you know, apply accordingly. So I'm going to have you guys do the other ones. You do need to have some sort of reference to find what these polyatomics are. I'll give you guys about 5 minutes to work through that. Okay. So this next one up here we have is zinc and sulfate. Zinc is a metal and its charge is 2+. It's not in the main group elements, but you've written it with a 2+ charge in your notes. Sulfate is SO4 with a 2- charge. Okay, where did I get that from? Out of thin air? No, I just have these memorized, but you will want to reference something. So flip-flop. So I should have 2 zincs for every 2 sulfates, SO4 with a 2. Now I'm going to reduce the 2 and the 2 down because ionics, you always go with the lowest common denominator. So I'll have ZnSO4. Don't leave the parentheses on there if you only have 1 polyatomic ion. Okay, sometimes people will leave those parentheses. That's not proper format. So we want to ditch the parentheses. We just have 1 sulfate. And if you're like, well, how do you know that it's sulfate? It doesn't look like a polyatomic if I don't have in parentheses. We know that it's sulfate. We know it is. This one here, calcium nitrite. Calcium Ca 2+. Nitrite, oh, it sounds really similar to nitrate. A little bit different, NO2 with a minus charge. One thing to note is your ITEs are 1 oxygen less than your ATEs. Okay, so if you know nitrate is NO3 minus, nitrite will be NO2 minus. If you know sulfate is SO4 2 minus, sulfite will be SO3 2 minus. The sulfur stays the same, the charge stays the same, the oxygen just drops down by a value of 1. All right, so we need to flip-flop. This has a 1 charge. Yeah, I didn't circle it here. Okay, this has a overall 2. That's where that came from. This has a 1 charge, so I'll have 1 calcium. This has a 2 charge, so I'll have 2 nitrogens and nitrates, NO2 with the 2 on the outside. Can't reduce those, so we're good there. Sodium phosphate. Sodium is Na with a plus. Phosphate is PO4 with a 3 minus charge. Okay, I'm going to packet this thing together, flip flop. So I need 3 sodiums for every 1 phosphate. Again, because I only have 1 of the phosphates, I just write it. I don't put it in parentheses. The last one, barium carbonate. Barium, Ba with a 2 plus charge. Carbonate, CO3 with a 2 minus charge. Group that together. This is a 2 to 2. So I know it's going to be 2 to 2. So it'll end up being a 1 to 1 ratio, or BaCO3. So you treat it the same way. You just, instead of using like nitrogen, you use a combination of atoms combined together with an overall charge. But the system is still the same of flip-flopping. Any questions on naming with a polyatomic ion? Or not naming, writing a formula with a polyatomic ion? Again, we haven't talked about the transition metals yet. We'll kind of leave that. Okay, so let's talk about how to name these things, because this thing is not aluminum plus nitrate. Okay, its name is aluminum nitrate. This thing isn't calcium plus nitrite. It's a calcium nitrite. And there's a way that we systematically name every single chemical formula we come into contact with. So this word nomenclature is just a fancy nomen. It's just a fancy way of saying naming. So the nomenclature is naming compounds. Because there's so many compounds out there, chemists had to come up with a system to name compounds. If you learn the rules to naming, then you can really name anything that comes your way, as opposed to like trying to nauseously memorize all the like tens of thousands of compounds out there. So many compounds will also have a common name, like H2O. Its common name is water. Okay, its systematic name is dihydrogen monoxide. Water, you do need to know H2O's common name is water. But for the rest of them, you don't need to know their common names. You will just need to know how to name them through the system, like through the nomenclature system that I teach you. They did one thing where they it was like this one of those like catch like how dumb Americans can be sometimes on the streets, and they were videotaping people and saying, do you know that they're putting dihydrogen monoxide in your water? Sign this petition. And all these people were like, oh my gosh, it's absurd. Not realizing that dihydrogen monoxide is water. It's just the formal name for water. If anyone ever comes up to you on the street and says that, don't be fooled. Systematic names, you figure out by knowing the system. Common names, you only learn through familiarity. There is no system to the common name. So when we're going to name something, you need to determine, is it ionic or is it molecular? If it is ionic, that means it's a metal and a nonmetal. This is how you're going to name it. Well, first you have to then pare it down even farther and say, is it a type 1 or is it a type 2 ion? Type 1 means that we have a predictable charge. So this is everything we've done thus far, from like column 1, 2, 3, and then zinc and silver. If the metal forms more than one type of ion, you have to do a little bit of extra work. This is for the transition metals. So let's go with the most basic thing here. We have a metal and one type of, just one type with one type of ion. There's the predictable charges. Okay, so I give you something. You're going to take the name of the cation. That's just a fancy way of saying metal. You're going to take the base name of the anion, that's the nonmetal, the base name meaning you take off the ending of it, and then you replace it with IDE. So this thing right here, NaCl, that is not sodium chlorine. It is sodium chloride, IDE, just how it is. Let's look at some of the base names for the nonmetals. So fluorine gets cut to fluor, or it would be fluoride. Chlorine gets cut to chlor, or it would be chloride. Bromide, iodide. I know that sounds weird, but it is iodide. Oxygen is not oxygenide. Okay, it's oxide. So we cut quite a bit of the oxygen off. Sulfur is sulfide and nitrogen is nitride. This is where things get interesting. So sulfide, right? Because there's so many, now there's like so many things circulating with the word sulfur as the root. We have sulfide, we have sulfate, we have sulfite. Oh my goodness. IDE is referring to the atom. So that's referring to sulfur with a 2- charge. ATEs and ITEs, that's where you go to your polyatomic ions. Sulfate is SO4 2-. Sulfite is SO3 2-. You may be thinking, really, is it that big of a difference if you call it aluminum sulfate versus aluminum sulfide? Yes, it's totally different. Aluminum sulfate has oxygen in it. It has different properties. So know your IDEs, right? Or at least know that IDE, for the most part, is talking about a polyatomic ion. Or I'm sorry, IDE is talking about an element. One exception is hydroxide. Hydroxide ends in IDE, but it is not talking about a single material like hydrogen. It is talking about OH-. So it's a polyatomic ion. If you wanted to ide hydrogen, it would be hydride. Okay, that is hydrogen on its own. So just, and this guy pops up all the time, hydroxide. So just know we're talking about OH-. There's so many little details with naming. It's like, the best thing I can say is practice, 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 practice to mastery. Really how we're going to get it. So let's name a couple things. I think going this way is easier than the other way. Whiteboard. And then after this, I think we will call it for the day. So I'm going to write some formulas and I want you to tell me what its name is. Al2O3. SRS. 3N2. KCl. Li. 2. S. Okay. So following the system, you name the metal, you ide an IDE. When I say ide, IDE, the non-metal. I'll give you all, this one should go a little faster. I'll give you just 3 minutes for this one. Okay, so you have a formula and you're going to try and come up with a name for each of these. This right here is a combination of aluminum and oxygen. It's a metal and a non-metal, so I always list the metal first, aluminum. And I don't call it aluminum oxygen. I truncate the non-metal and I ide it. So it's aluminum oxide. Aluminum oxide. This here, SR is strontium. The second thing is sulfur. Well, I'm going to ide it, sulfide. Strontium sulfide. It's not really that complicated. Hopefully this feels kind of simple compared to the other way. Zinc combined with nitrogen should be zinc nitride, IDE. Again, all these ending in that IDE. This one here, K and Cl, that is potassium chloride. Last one here, lithium sulfide. Betsy asks, so the subscripts do not affect the names. In this case, they do not, okay? These are all type 1 ionic, meaning that the metal has a predictable charge. In that case, if the metal has a predictable charge and it's ionic, you don't need to take into account the subscripts. Why? Well, when a scientist writes a name, they want to put as few characters down as possible. They want to be able to represent it as simply as they possibly can. So they need to put that there are 3 zincs and 1 nitrogen. No, because if I wrote this, zinc nitride, could I get back to this formula? Well, zinc always has a 2+ charge. Nitrogen always has a 3-, flip-flop. The only option is this right here, which is this. So this is more than enough information to get you back to the formula. Does that make sense? I don't need to say, hey, zinc 2, or rather zinc 3, nitrogen 2, because just saying zinc nitride gets me right back to my formula. Same thing with like lithium sulfide. Okay, I don't have to, when you're looking at this here, if I just gave you this, could you get back to this formula? You could. Lithium is Li with a +1 charge, sulfur has a 2- charge, flip-flop, Li2S. You are getting the same thing. That doesn't work when you have a varying charge, which we've sort of like stayed away from. But let's look at one example. If I write something like, what did we say earlier? Didn't we say like titanium and sulfur or something? I don't know. Titanium sulfide. Can I come up with a formula? Not when it's written like this. What I need is a Roman numeral after the titanium that tells me what its charge is. So is this titanium with a 1 charge? Is it titanium with a 2 charge? Okay. Is it titanium with a 3 charge? So you will have to write that in. If it's titanium with a 3+ charge, now I can come up with a formula because titanium I know has a 3+ because it's written here with the Roman numeral. Sulfur is always 2-, flip-flop. I'll have 2 titaniums for every 3 sulfurs. So that's how transition metals or type 2 with varying charges differ from our type 1s. In our type 1s, it's simple, easy, clean. Type 2s or varying charges, we have to include it in the Roman numeral. So, why don't we'll take a quick peek at it and then we'll call it for today. So we're in a good spot for next week. So sometimes they're called binary ionic compounds. Those are metals that have varying charges. When you name them, you must specify which charge you're dealing with in parentheses. So if it's copper with a 1+ charge, you have to call it copper Roman numeral 1. We don't drop the 1 with the charge. All right, keep that there. If it's copper with a 2+ charge, it'll be copper 2. What if it was copper with a 3+ charge? It'd be copper Roman numeral 3. What is the highest charge an element can have? Cynthia's asking. Traditionally, we see it like 4s. But you can have hypothetical situations where they make it even more than that. Okay. So you don't have to have them memorized. I don't expect you to know that copper has two different varying charges, 1 and 2, or that tin is 2 and 4, because you'll always be able to figure it out. And I'm going to show you how to do that right now. No. Well, yes, I'll be done in a couple minutes. Okay? Sorry, hold on 1 second. She's like, Daddy won't let me do the iPad. So then she sneaks in and asks me. I'm like, no, we're a unified front here. You're not going to get into get between us like that. That's the one really good piece of advice my mom gave me. She's like, you have to be a unified front with your partner, at least when the kids are around. You can argue about it later, but when they're there, you're on the same page. Okay, so we'll do one of these just so you can kind of get the idea. Maybe two. Let's say I have a chemical formula like this, FeO2. And I want to name this thing. So this one is a little bit different, right? In that it's a metal. It's a non-metal, but the metal has an unpredictable charge. So instead of writing iron, I have to write iron, and then I'm going to put like a set of parentheses and come back to that. Okay, so I'm going to write iron. I know I need to include a charge, and then I'm going to write oxide. So sort of like the skeletal formula or name. So how do I figure out what the charge is on iron? Well, do you guys all agree that the charge for this whole compound is 0? We don't see a charge in the upper right-hand corner. So the whole charge has to equal 0. So I'm going to cut this thing in half, sort of, and separate it into the metal half and the non-metal half. You go from what you know for sure to get what you don't know. What is the charge of oxygen? Oxygen always has a charge of 2-, doesn't it? Where its column is. How many of them do we have? We have to multiply that by 2 because there's 2 of them. So this is a 4- charge. So the overall charge of the oxygen is 4-. So what does the iron have to be to balance that out? It has to be equal and opposite, 4+. So this is going to be iron 4 oxide. Instead of FeO2, what if I wrote FeO? This is also an iron oxide. These are like all of these things are kind of a group called iron oxides loosely. So it's iron, Roman numeral, oxide. How does this one differ from the first one though? The charge is going to be different. So the overall charge still needs to equal 0. Let's cut it in half. Oxygen always has a 2- charge. That doesn't change. How many oxygens do I have? I only have 1. So my overall charge, so we'll multiply that by however many I have is 1. So my overall charge is 2-. So what does the iron have to be to balance out a 2-? It needs to be a 2+ charge. So this would be iron 2 oxide. Let's do one more. What if we have Fe2O? And it's like, oh man, those things look so similar. Aren't they like the same thing? They are not. This is also an iron oxide. Let's find its charge. What's going on here? Oxide. Let's cut it in half. Oxygen, well, the whole thing needs to equal 0. Oxygen is always a 2- charge. And there are one of them. So it's an overall 2- charge. So the totality of this side needs to be 2+. But how many irons are there? The 2+ needs to be distributed amongst 2 irons. So we're going to take this and we're actually going to divide it by the 2. Right? So divide it by the 2 to get a 1+, or each iron gives you a +1 charge. So this would be iron 1 oxide. And a lot of people will go, well, I don't think that's right. I think it's iron 2 because there's 2 here. So it should be 2. Okay, well, one way you can check is to go backwards. Let's write out the word or the name iron 2 oxide. Iron would have a 2 plus charge in this case. Oxygen would have a 2 minus. Flip flop, we get FeO. It's not the same thing. So it is incorrect. This one, iron 1 oxide, would be Fe with a 1 plus, oxygen with a 2 minus, flip flop, Fe2O, ding, ding, ding. They are the same. So you can revert in the other direction. So I'm going to stop there. We will definitely do more of practice with these next time. And I'm going to like jumble them all together. Okay. So we're going to do metals with predictable and unpredictable. And then we're going to throw some non-metal stuff in there as well. We'll put polyatomic ions and we'll have like all sorts of fun.